So today I'll be discussing two papers that approach the same idea but from two different angles, which is how can we improve student learning through understanding data. The first paper is using learning analytics to develop an early warning system for at-risk students, and then the second one is hierarchical Bayesian knowledge tracing in undergraduate engineering education. So the first paper by Akpinar and al. Applies to supervised learning to develop an early warning system that predicts student success in an online course. It's built on classification models such as K nearest neighbors, naive Bayes, decision trees, and random forests. And it applies these models to learning management system behavior data such as logins, quiz attempts, and time spent, and then reports the standard confusion matrix metrics, and then evaluates the models across weeks 3, 6, 9, 12, and 14. Sun's paper, on the other hand, uses a hierarchical Bayesian knowledge tracing model, or HBKT, and it's an extension of the standard Bayesian knowledge tracing framework, which is designed to capture how learners' underlying mastery states evolve across time and skills. It jointly estimates student ability and skill difficulty and uses a maximum a posteriori map estimation with partial pooling for interpretability and stability. So while Akpinar's paper demonstrates data-driven prediction using bias variance control, Sun's model shows a model-driven inference through hierarchical Bayesian estimation. So starting with Akpinar's methodology, the author used weekly LMS data from over 100 students, which generates nearly 50 features per week. And then because the sample size was pretty modest, they adopted cross-validation to control estimator variance and then employed feature selection using Gini importance to retain the top 10 predictors each week. Each model was tuned across a grid of hyperparameters, and then the best model was chosen by a mean fivefold cross-validation. The top performer, which it was KNN with equal width discretization, achieved the best bias variance balance. And then the discretization step was meaningful because it converted continuous variables into a few bins, and then the model trained a bit of bias for substantially reduced variance, which is essentially an operational form of the bias variance trade-off. So looking at Sun's framework, he took the traditional knowledge tracing, which assumes students share identical parameters for learning and forgetting, and he introduced hierarchical priors over student and skill level parameters, which allows estimates to borrow statistical strength across groups. And then each student's ability, beta S, and each skills difficulty, BK, are drawn, or beta K, are drawn from shared population level distributions. He used a maximum a posterior map estimation, which is implemented via LBFGSB optimization algorithm instead of a full posteriori with Markov chain Monte Carlo, just because the MCMC would be computationally expensive. And then it minimizes the negative log posterity, and then it acts as like a ridge regularized logistic regression. Sun also evaluated the model with a log loss and AUC, or area under the ROC curve, where log loss measures the average cross entropy between predicted probabilities and actual outcomes, where lower is better, and then AUC evaluates ranking quality, or how well the model discriminates between correct and incorrect responses across thresholds. So looking at Akpinar's results, by week 3, using only the early behavioral data, the KNN classifier achieved a 74% accuracy with sensitivity and specificity both near 0.73. And then by week 14, the accuracy climbed to 89%, where the final confusion matrix shown in figure 2 shows a precision of 0.89, a recall of 0.75, and an F1 of 0.81. So the accuracy stabilized really early, which indicates that a small sample of weekly features contains a really good predictive signal, where adding additional data doesn't add a lot of new information. So looking at figure 3, it shows the predicted success probability versus total attempts, where 3 clear stratas emerge, where these high efficiency learners exceed 0.8 probability with a couple of attempts, which indicates low posterior variance, typical learners fall between zero point 0.4 and zero point 0.8, which follow a diminishing return curve consistent with log linear um, learning process, and then low performers stay below zero point 0.4 despite a lot of attempts, showing high residual error and low information gain. So the error variance changing with attempt count justify the local nature of K&N, which adapts to subgroups without assuming homogeneity. And then figure 4 examines the model calibration, where predicted versus observed success rates fall almost perfectly along the diagonal, confirming the probabilities are well calibrated. And then only at the extremes do we see like a mild over or under confidence, which kind of shows the small number of false positives and false negatives shown in the confusion matrix. So this shows a deliberate type 1 and type 2 error trade-off where the model tolerates a few false alarms to minimize missed at-risk students, which is an appropriate decision in an educational setting. So switching over to Sun's hierarchical Bayesian model, it produced interpretable posterior estimates for both students and skills, where the population means were roughly mu theta equal to 0.09 for ability, and then mu beta for negative 2.4 for difficulty, where standard deviations were 7.3 and 3.3. These wide spreads indicate a strong heterogeneity, which is what we want with hierarchical shrinkage. So, looking at Figure 5, it ranks skills by difficulty based on posterior means, where the easiest skill, like vector addition, show high predicted probabilities, while the hardest concepts, such as equilibrium in 3 dimensions, show low predicted probability. So, what's important is that the correlation between observed and predicted success rate validates the model's probabilistic assumptions that align with the empirical frequencies. So now looking at figure 6, it shows the predicted correctness over repeated attempts for one of the lowest ability students. And despite the 300 responses, the predicted probability kind of plateaus right around 0.4. And it illustrates that the model captures not just the noise, but actual meaningful persistence of low ability, which kind of shows the posterior stability of the model. Compared with a non-hierarchical logistic regression, the HBKT model achieved higher AUC and lower log loss on held-out data, which means that it was both better calibrated and more discriminative, which is pretty rare. The reason for the partial pooling is that the priors add enough bias to reduce estimator variance, improving the mean squared predictive error. So essentially, the posterior mode serves as a regularized estimator of each student's ability, and then this regularization shrinks outliers towards the population mean, which reduces overfitting. So now that we've gone over both studies, it kind of illuminates the same topic from just different statistical landscapes. So first, the choice of metric defines kind of what success means. Akpanar's team used accuracy, sensitivity, and specificity, which is like frequentist estimators of classification quality, and then where each corresponds to an underlying conditional probability, and then their interplay shows how model evaluation trade-offs between type 1 and type 2 error is important. And then Sun used an AUC and log loss, which are expectations over predictive distribution, and they're grounded in probabilistic modeling. These summarize not just the discrete classification outcomes, but continuous confidence calibration. So the second thing, where both demonstrate ways to control variance. Akpanar does it implicitly through cross-validation, discretization, and feature selection, where Sun does it explicitly through Bayesian priors and hierarchical pooling. In both cases, the statistical goal is identical, where you have to balance bias and variance to minimize expected generalization error. Third, they highlight interpretability as a statistical property, not just a design choice. In the early warning model, interpretability comes from transparent metrics and simple decision boundaries, while in the HBKT model, it arises from structured parameters such as ability and difficulty that have direct theoretical meaning. So to summarize, both papers demonstrate the maturation of educational analytics as a statistical field, and it shows just how important statistics are in the education. department.